Unit 6, Chapter 23, two sample t-test and interval. I also am going to include smoker versus non-smoker example. That's included in your packet. All right, let's take a look. Okay, so for the first thing here, we're going to be comparing two means. So let me get one here that's a little cleaner. There we go. Okay, so for comparing two means, basically the biggest thing that you're going to have to look out for, and I want you to see, is that you have two populations. In the random sample, you have a random sample from two populations, and those populations are independent from each other. That's the big thing for you to see. Now, same thing like what we learned about in the sampling in the sampling procedures for a one sample t-test are true for two sample t-tests. We have a problem, and that problem is that we don't know sigma. And so instead we use S. But because we don't know sigma, we cannot use Z, we have to use T. So that's going to just change things just a little bit. So let's go ahead down here. You can read through these notes. That's basically what I just said. But we're going to go ahead and do our phantoms. So for our phantoms, the first P is for my parameter. And the parameter is going to be for two sample T is mu1 equals. And notice we're looking for observed differences. And that is going to be the true mean difference, or you can actually call it difference of means, really. True mean difference or difference of means, because that's what we're doing, and then whatever my stem is. For mu2, you're going to use the same exact thing, and then whatever my stem is. By the way, you are allowed to use air quotes for this as long as you change. Like if this was for whatever we're talking about, but let's say we're talking about boys, and this was talking about a group of girls. So you would make sure that you could use air quotes because it copies everything except those two things. Okay, so that's my P, which is parameter. Secondly, my H, which is my hypotheses. We are starting to assume that the two populations are the same. And the populations are the same. You can write it either as mu1 equals mu2, or the difference in mu1 and mu2 is equal to 0. So my alternative hypothesis is either going to be not equal to, greater than, or less than. Remember, when it's not equal to, I'm going to have a T procedure that is on both sides. When it's one-sided, it's going to be greater than. It's going to just be, this one here would be greater than. And then this here would be a less than for my ha. And then, of course, the blue one, which has both sides, is going to be a ha is not equal to. Okay, so before you can continue, you have to check your assumptions and conditions. So my assumptions are going to be my random and my independent. You have to check if it's a random, and make sure you tell me if it's a random sample or if it's a random assignment. Random sample is how you're collecting it, that I have, let's say, 4 cards or 5 cards, and I want to collect a random sample for these, and I randomly choose with a random number generator, let's say number 2 and number 5. That is a random sample. Then let's say I want to try to see if bleach can clean this better than ammonia. And so I flip a coin, and I have heads or tails, where bleach is the heads and ammonia is the tails, and I flip a coin, and I'm saying, oh, okay, I got heads for this one, so this one gets bleach. Let's say I get tails for this one, so that one's going to get ammonia, but you flip the coin to see which one goes where, and that would be random assignment. So when you say random, you cannot just say random. You have to put random sample or random assignment, and make sure you say that it's given. You can't just put it. Independent, of course, you're going to see, are they independent? That's really, really important. You must see that these two samples are actually independent from each other. And so, because that's the main thing, that's why they make them two samples. If they're not independent from each other, then we have what's called a paired t-test, which is on another video. All right, large sample. A large sample, we have to do the main thing for the same thing that we've done for the large sample. And, oh, that's not down here. I was thinking it was down here. But the large sample is the same thing that we've been doing, and that is going to be for n each one, you have to have N1 and N2 has to be greater than 30. And if it's not greater than 30, you're going to have to show that it's unimodal, symmetric, and has no outliers. Now, the no outlier part is just for the small one and the small sample, which is less than 15. If it's between 15 and 30, you just have to show unimodal and symmetric. The way you would do that is either it's going to give it to you that it is unimodal symmetric, or you're going to have to draw a histogram or a box plot, and you're going to have to make sure you label and just do, let's say, this number of pairs of shoes. And then you would say, okay, unimodal, symmetric, no outliers, and you'll set, and therefore, once your conditions have been met, because that, the 10% rule, sorry about that, 10% rule, and the 10% rule shows that I took 10%, I only took less than 10% of the population. And if all those conditions are met, then I am safe to proceed to a 2-sample t-test. Now I have to do my degrees of freedom. For my degrees of freedom, just use your calculator. There are complicated ways to find the degrees of freedom. We're never going to use it, never going to find it in this course, so just use what's on your calculator or what they give you. Okay, so what I talked about just up here just a bit is the same thing, is that because I don't know my sigma, I'm going to have to use my S. But remember here, how do I get this? Is it shows, that's the work it shows up here, is how do I get this? I cannot add S1 plus S2. I cannot do that, so I have to add the variances. And this is going to be S over square root of N squared plus S2 over square root of N2 squared. The reason I have S over square root of N, because if I look in my formula chart to begin with, remember, if you see for a 1-sample t-test, remember my standard deviation is equal to S over square root of N. So that's where I get that from. Well, now I have to add them together, but this still gives me the variance, so I need standard deviation, and then I'm left here with this here. If you walk this through the formula chart, you'll be able to see that this here is on the formula chart. All of these areas are on the formula chart. So I'm going to talk you through the formula chart. So if you get your formula chart out, or I'll take you through it and see. Let me take you to the formula chart. All right, if you go to the back of the formula chart, you can see I have in green the highlighted part for the 1-sample, but this is for 2-sample. And here you go. Remember, let's look back at what you said. What I had was, it was x1 minus x2 minus mu1 minus mu2 over, and this is the equation we're doing right here, s1 squared over n1 plus s2 squared over n2 and the square root of that. Now, this one, if you notice, is the exact same equation, except this is standard deviation, population standard deviation. This is standard deviation of a sample. But I don't want you to put these in. I want you to actually just use numbers, because then you'll get the correct answer. If you put sigma and you need to put S, you'll get the wrong answer. All right, so that's how you find on your formula chart. And then, so once you have your T, of course, you're still going to draw your picture, and it's going to be your T degrees of freedom for your model. And this is still labeled as 0 because this is a standardized model, and whatever your T is, you're going to put it on your model, and this here is going to be your p-value. Okay, so let's go ahead and run through one and see if we can make it make sense. Resting pulse rates for a random sample of 26 smokers has a mean of 80 beats per minute and a standard deviation of rest of 5 beats per minute. If you notice, I labeled them already in pink, and S is the number of the number of smokers. X bar S is the mean of the smoker's heart rate, and then SS that I have is the standard deviation of smokers. I did the same thing for non-smokers, and then I look and see, it tells me already it's roughly symmetric and has no outliers, so that's great. And then, is there evidence of a difference? Is there evidence of difference means my HA is going to have a not equal to, because it doesn't say greater than, it doesn't say less than, just wants to know if there's difference. Okay, so let's go ahead, and I'm going to jump over to where the answers are on another form. This one. Here we go. All right, so We're going to start here with mu n is the true mean pulse rate of non-smokers, and mu s is the true mean rate of smokers. Guys, you are welcome to use 1s and 2s instead of n's and s's. It's up to you. Doesn't matter. Okay, so my HO is going to be mu1 equals mu2. That's the way my HO is always, or you can have mu1 minus mu2 is equal to 0. Either one is acceptable. My HA is not equal to, because we looked at here, this said difference. Now I'm going to check my RILT, random sample. Both, you have to make sure you say both. Both non-smokers and smokers took our SRS, that's given. Independent, the populations of smokers and non-smokers are independent from each other. They're two independent populations. Large sample, they're not a large sample because they're not bigger than 30, just, well, one of them is. But it doesn't matter because the whole idea of large sample is that it's approximately normal, and it gives it to us that it's approximately normal. So that's all I have to say, is that when it comes to a large sample, I just say both are stated roughly symmetric, no outliers. I check the 10% rule, and I check for them for both. And then I'd say conditions are met for 2 sample t-tests for about approximately normality with a degrees of freedom of 55.95. All right. So now I do my T procedures. This T procedures is just, this is my X bar 1. This is my X bar 2. And then this, of course, is S1. This is N1. This is S2. And this is N2. And guys, this formula is just exactly what I just showed you from the formula chart. Don't put the U symbols, use the numbers. So then I go ahead and draw my graph. With this, I'm just going to point out to you to make sure that you put your T, degrees of freedom. You label your P. It's two-sided because of this here, because this is not equal to. And you shade the right side, and then you say, okay, my p-value is really, really, really tiny. So since the p-value is really small, I'm going to reject HO, and that means I do have evidence. Since I do have evidence to reject HO, I do have evidence to say that I do have evidence to state HA, which is that there is evidence that the pulse rate has a change. Okay, remember it says how much of a change, or nope, I apologize, it didn't say how much of a difference. But the next one asks you how big of the difference is there. And whenever it asks how big of a difference, you're looking for a confidence interval. And so since I had a alpha as a 5%, or excuse me, yes, alpha was 5%. What that means is both sides total for my alpha was equal to 5%. So that would mean the middle's left at 95%. So my confidence interval should be 95%. Okay, so I'm going to go ahead and solve how big the difference. The P and the A we did already above. We're going to name the test. And the test is called a 2-sample T interval with a degree of freedom of, right here, 55.953. We're going to have then this, let's jump over to our formula chart, and I'm going to show you where this is. This is X bar 1 minus X bar 2, which we kind of talked about that. T star, and then that's my standard deviation, the S squared over N1, and then plus S squared, S2 squared over N2. And those, let's jump back to our formula chart and see what we have. So that's the same thing that we just kind of found out here was, remember, this is the X1 minus X2 plus or minus the T star over this formula here. If you're not sure, your confidence interval is right here. Statistic, this is for a different one. And the statistic in this case is X bar 1 minus X bar 2 plus or minus the T star, degrees of freedom, which I just showed how to use a T-star in another video, but I'll show this one too. And standard error, that's what the square root of S1 squared over N1 plus S2 squared over N2. That's what that is. All right, and you can see that's just in green what I circled here. Let's talk about how to get T star. On T star, if I go to my, hold on, 55.953. Okay. If I'm doing a 95% confidence interval, so I have to put in to my inverse T a area of 0.975. Remember, because the calculator starts here at 0 and you have to calculate that extra bit. And the degrees of freedom is 55.953. So I'm going to go to my calculator and I'm going to go menu, distribution, inverse T, and I have 0.975 and degrees of freedom I think it was 953. I'm not sure exactly, but around 2.003. And that's what we got here. So that's where this comes from. 80 minus 74 plus or minus 2.03, and then that's my standard deviation. Guys, don't write the formula out. Don't write that out with the symbols. Only put the numbers in. It's not wrong to put the symbols, but if you put the wrong symbols, it's wrong, and you don't want that. Okay, you're going to run this in your calculator. And to put it in your calculator, I did not show you how to put this in your calculator. I apologize. That's where I got all the information from. I mean, well, no, I guess I did put it in by hand, but you can also throw this into your calculator under this here, menu stats 2-sample t-test. So I'll run this one and I'll run this one. This one here's menu stats interval. And this is a 2-sample t-interval. So this one says menu stats. And we are doing, wrong one, sorry, menu. There we are, stats, test. This is for the first one. And that would be a 2-sample t-test is what we were doing. And I don't have data, I have statistics. So, okay. And I'm just gonna fill all these in. And that, if you remember, I'm just filling it all in. I'm going back up here. And that was 26, 80, and 5. So 80 is this, 5 and 26. And this was, the data was 74, 32, and 6. So 74, 30, or 6 and 30. And it was a not equal to, and it's not pooled. It's never pooled. Always put no with means. And that's all the data that I got. My t and everything else, the small p-value. So that's what I got on here. And for the interval, very, very similar. Instead of doing test, I just go menu, stats, interval, and then I do a 2-sample t interval. And instead of data, I do stats. And it'll be the same thing. So it looks really similar. So I'm going to put in 80... 5, 26. Am I remembering right now? I'm forgetting. Yeah, I got it. Okay, and then 74, 6, and 30. Or was it 32? Let's just double check. It was 32. Okay, and then I'm doing a 95% confidence interval. So I just put 0.95, and no, it's not pooled. And there's my data, everything that I have and everything that I need, 3.1 to 8.89. And that's what I have here, 3.1 to 8.89. And then I just write we are 95% confident that the true difference of pulse rate of mean 1 minus mean 2 lies in the interval of 3.1 to 8.89 beats per minute. Now guys, 0 is not in the interval. And so since 0 is not in the interval, that 0, by the way, came from my HO and the other problem right here. And it's not in the interval, so it also would be a reject, which is the same problem that we have, or the same conclusion. All right, I hope that helps you determine between a 2-sample t and a paired t. Remember, on a 2-sample t, one thing, if your sample size, if N1 is not equal to N2, you definitely know that it can't be a paired t, So it's a 2 sample T. But we do have a lot of N1s that equal N2. You know, this both side is the same, but that doesn't mean it's paired. It just has to be. The samples have to be the same size because they're paired. You know, you're going to out with a date, and if nobody shows up, you're not on a date. You're alone. As a pair, you're not a pair unless you're with someone. Anyway, so that's what the paired is going to be. So you have to make sure the paired. But I can have, just like I could have 30 women and I could have 30 men, and that could be a 2 sample. I could be comparing the average person or the average woman that likes gory movies, like violent movies, versus the average number of men that likes, in a high school or something, that likes violent movies. And then we can compare those, right? That's 2 samples because the populations are 2 separate populations. The random samples are also separate. All right, guys, I hope that helps. Do well.